Hello and welcome to tutorial 16. Our topic today is an introduction to organic chemistry and nomenclature of hydrocarbons. Before we get started, just a quick reminder that the notes to accompany this video tutorial are available online through my website. And with that said, let's go ahead and get started. Organic chemistry is the branch of chemistry that deals with the study of carbon-based compounds. So you might be thinking, well, carbon is just one element out of over 100 in the periodic table, so maybe organic chemistry is just a small branch of chemistry. That would not be correct. There are over 18 million known organic compounds, and more are being synthesized and discovered every day. So this is not a small branch of chemistry. So we're going to go ahead and get started with a little bit of review from an earlier tutorial. We're going to look at the ways in which carbon bonds to other atoms. So you might recall that carbon, being that it's a group 4 element, has 4 valence electrons. I'm going to go ahead and draw them as a dot symbol here. And so carbon can form 4 single bonds. And remember that although we write these bonds as if they're 90 degrees apart in three-dimensional space, that's not really an accurate picture of the three-dimensional orientation in space. Remember that these 4 charge clouds would repel maximum distance apart. And the maximum distance apart that they can get in three-dimensional space is 109.5 degrees. So I'm going to go ahead and redraw this to show that 109.5 degree bond angle, which means that this bond would be coming out at us and this last bond would be going away from us into the plane of the whiteboard. And let's go ahead and label, go ahead and use a red pen here, label that bond angle as 109.5 degrees. And you might recall that we said that the molecular geometry about this central atom, this carbon, would be referred to as a tetrahedral. So I'm going to write that here. But carbon can also share those 4 electrons in a different way. Carbon can form a double bond and 2 single bonds. And the bond angle between those 3 charge clouds, 1, 2, 3 charge clouds, would be, again, maximum distance apart in three-dimensional space, 120 degrees apart. And you might recall that we referred to the molecular geometry about the central atom, in this case about this carbon, as being a trigonal planar geometry. So I'm going to go ahead and write that here. Trigonal planar molecular geometry. Another way that carbon can share its 4 valence electrons is in 2 double bonds. That means 2 charge clouds. Maximum distance apart in three-dimensional space that 2 charge clouds can be is 180 degrees. For a linear molecular geometry. And finally, carbon can share its 4 valence electrons in a triple and a single bond. Again, 2 charge clouds. The triple bond counts as 1 charge cloud and the single bond counts as a charge cloud. Maximum distance apart in three-dimensional space that those 2 charge clouds can be, again, it's 180 degrees, leading to a linear geometry, linear molecular geometry about that carbon atom. Now, carbon can be bound to, in these examples, other carbon atoms. It could be bound to hydrogen. It can be bound to other atoms as well. The most common other atoms that we're going to see in biological chemistry are nitrogen, oxygen, and sulfur. So you can start to see a really wide variety of molecules that you can come up with already in your mind, looking at these different bonding patterns and imagining them bound to carbons, imagining these carbons bound to oxygen or nitrogen or sulfur. So the possibilities start to really add up. So we're going to go ahead and start with the simplest type of organic molecules, those that contain carbon and hydrogen only. These are called hydrocarbons. So let's go ahead and erase here and talk about hydrocarbons. So hydrocarbons, again, contain just hydrogen and carbon. So I'm going to write here hydrogen and carbon only. And hydrocarbons can be either saturated or unsaturated, where these terms are really referring to the quantity of hydrogen in the molecules. So let's start out by talking about saturated hydrocarbons. In a saturated hydrocarbon will contain the maximum number of hydrogen possible per carbon atom in the molecule. So let's write here, contain max number of hydrogen atoms per carbon atom. And this is because saturated hydrocarbons contain just carbon-carbon single bonds. It's right here, contain carbon-carbon single bonds only. And the more specific term for a hydrocarbon that is saturated with hydrogen is alkane. We call saturated hydrocarbons alkanes. And alkanes will always follow, except for cyclic alkanes, alkanes will always follow this general formula. They will follow the formula CN, where N is the number of carbons, H2N plus 2. So the number of hydrogen will be 2 times the number of carbon plus an extra 2 for the terminal carbons. So let's go ahead and take a look at an example of a molecule, a saturated hydrocarbon with just 2 carbon atoms, single bond in between them. Now, how many hydrogen can each carbon then have? The maximum number of hydrogen possible per carbon would be 3 on each side. To complete octet here, we could have 3 hydrogen. Okay, so 3 hydrogen atoms. And we see the same thing on the other side for the other carbon. Let's go ahead and draw those in. Complete our octet here. 4 bonds to carbon, 4 single bonds. And let's take a look at this formula. So in this case, N is equal to 2 for the number of carbon. So we've got C2, and H is going to be 2 times 2 plus another 2. So this formula, the molecular formula for this molecule is C2H6 for the 1, 2, 3, 4, 5, 6 hydrogen. And that's the maximum number of hydrogen possible per 2 carbons, total of 6 hydrogens. Okay, so let's go ahead and take a look at unsaturated hydrocarbons. Unsaturated hydrocarbons contain fewer than the maximum number of hydrogen atoms possible per carbon atom in the molecule. So we're going to write here, contain fewer. They are not saturated with hydrogen. They contain fewer than the maximum number of hydrogen atoms possible per carbon atom. And this is because your unsaturated hydrocarbons will contain either carbon-carbon double or carbon-carbon triple bonds. That's right here. They contain carbon-carbon double bonds. The more specific term for an unsaturated hydrocarbon that contains carbon-carbon double bonds is alkene. I'm going to write that here. Or carbon-carbon triple bonds. The more specific term for an unsaturated hydrocarbon that contains carbon-carbon triple bonds is an alkyne. Okay, so let's talk a little bit more about alkenes first. So I'll write down here alkenes. An alkene that has one carbon-carbon double bond will decrease in the possible number of hydrogen by 2. So an alkene with just one carbon-carbon double bond will follow the formula CnH2n. Okay, so 2 fewer hydrogen than the corresponding alkane. So let's take a look at an example, and again, let's just use the 2 carbon example, but now we have a double bond between those 2 carbons. Well, how many hydrogen can we have? How many hydrogen is it going to take to achieve octet for these carbons? Well, we can probably see already that it's going to take 2 hydrogen atoms to achieve octet. Same thing over here. So I'm going to go ahead and draw in those hydrogen. Okay, and my formula, because I have N equal to 2, is C2H2 times 2. Or my molecular formula is C2H4. So 2 fewer hydrogen than the corresponding alkane with only 2 carbons. The alkynes will have even fewer hydrogen. So for an alkyne with just one carbon-carbon triple bond, the number of hydrogen will decrease by 4. In comparison to the corresponding alkane. So it's going to follow the formula CnH2n minus 2, 4 fewer. Okay. So let's take a look at the alkyne with just 2 carbons, so a triple bond between them. So how many hydrogen can this carbon have? Only 1. 1 hydrogen to achieve octet. Okay, so I'm going to go ahead and draw that in here. It's going to be the same thing on the other side. Okay, so again, N is equal to 2 in the example we're using here. So C2, H is going to be 2 times 2 minus 2. Or in other words, our molecular formula for this compound is C2H2. 4 minus 2 is 2. Okay. All right, final word before we go on from here that you probably have heard the terms saturated and unsaturated with respect to your foods, fatty acids in your food. So what they're referring to there is really what we just discussed here, except they're referring it to this with respect to the fats. So they're referring to the hydrocarbon portion of your fatty acid molecules, which actually have another functional group on the other end, but the hydrocarbon portion of those fatty acid molecules can either be saturated with hydrogen, contain just carbon-carbon single bonds, or that hydrocarbon portion of the molecule can be unsaturated. And in the case of fatty acids that are naturally occurring in our foods, they just have carbon-carbon double bonds. They don't actually have triple bonds. So your unsaturated fatty acids contain one or more carbon-carbon double bond. And if they are monounsaturated fatty acids, then they contain just one carbon-carbon double bond. If they are polyunsaturated fatty acids, then the hydrocarbon portion contains multiple carbon-carbon double bonds, poly. Okay, so just a little interesting foreshadowing of things to come when we get to more details on the structures of fatty acids. All right, let's go ahead and erase here and go on to slide number 3. So we are on slide 3, nomenclature of straight-chain hydrocarbons. So the first thing I want to address is what I mean when I say a straight-chain hydrocarbon. So we learned that carbon can form 4 bonds. Okay, so I'm just going to use a 4-carbon example here. Well, we can have 4 carbons connected all in a row, like so. And I'm just using a saturated hydrocarbon as my example. So I'll just go ahead and saturate all those carbons with hydrogens. But those 4 carbons can be connected in a different way, where there's only 3 in a row, and then we have a carbon branched off of that second carbon in the chain. And this is what we would call a branched hydrocarbon. Okay, so again, all of my carbons are saturated with hydrogen. Go in and draw them all in. Okay, but this is what we would refer to as a branched hydrocarbon. We're just focusing right now on straight-chain hydrocarbons. Okay, so I'm going to go ahead and erase those 2 examples, and we're going to talk about how to name straight-chain hydrocarbons. They're the easiest ones to name. So to name a straight-chain hydrocarbon, all you need to know are prefixes that tell you the number of carbons in the chain. Okay, so you need a prefix. Tells the number of carbon in the chain. And then to that prefix, you're going to add the appropriate suffix that will tell you whether or not you're talking about an alkane, an alkene, or an alkyne. It tells if alkane, alkene, or alkyne. And that's pretty much the gist of it. So let's take a look at the first 10 prefixes, which represent from 1 carbon to 10 carbons. We won't go beyond 10 for these tutorials. Okay, so let's write them down here. And they are also written on slide 3 for you. Okay. The prefix meth tells you 1 carbon. Eth is 2, prop is 3, bute is 4, pent is 5, and go up here, hex is 6, hept is 7, oct is 8, non is 9, and dec is 10. Okay, so these are our prefixes, 1 through 10. And the suffixes that you're going to add are simply the A-N-E ending if it's an alkane, the E-N-E ending if it's an alkene, and the Y-N-E ending if it's an alkyne. So I'm going to erase here and let's look at a couple examples. Okay, so let's go ahead and just do these three problems. We're going to put the appropriate prefix to specify the number of carbons in the molecule together with the appropriate suffix to tell whether or not it's an alkane, an alkene, or an alkyne. All right, so this first molecule has just one carbon, so the appropriate prefix for one is meth, and one carbon can only have single bonds to hydrogen, so this is methane. Okay, the next molecule has two carbons, so check slide 3 if you need to and determine how many or what prefix to use to specify just two carbons. The prefix we want here is F, and because this is a carbon-carbon double bond, the suffix that we want is to reflect that it's an alkene, so we want to call this methene, E-N-E ending, not ethane, which would be for the molecule with two carbons. It just has a single bond between them, not a double bond. All right, over here we've got 1, 2, 3. 3 carbons. The appropriate prefix is prop. We've got a carbon-carbon triple bond. So this is not an alkane. This is not an alkene. This is an alkyne. So we want the ending to be Y-N-E. The name for this molecule is propyne. All right, so I should mention here that this is IUPAC nomenclature. That stands for International Union of Pure and Applied Chemistry. So your instructor may refer to some molecules with common names. Of course, double check with them and make sure that you know which common names you need to know. Most of the time you'll be using IUPAC nomenclature, I would assume. All right, so we're going to go ahead and erase these 3 examples, and we're going to talk a little bit about isomers, which is on slide 4. Okay, so when you have more than 3 carbons in a chain, when you have 4 or more carbons, and you have an alkene or an alkyne, there's going to be multiple locations for that double or triple bond. And so we have to go a step further when we're naming alkenes and alkynes with more than 3 carbons and specify the location of that double bond with a number written before the prefix, written before the molecule's name. Now we call molecules that have the same molecular formula but a different connectivity of atoms like this isomers. Specifically, we call them constitutional isomers. Some books will call them structural isomers. Hopefully that's not too confusing there. So let me write this up here. Constitutional isomers. Constitutional isomers are molecules with the same molecular formulas but a different connectivity of atoms. Okay, and I'm going to write in parentheses here, they're sometimes also called structural. Structural isomers. So I'll write that in parentheses. So let's take a look at an example of a 4-carbon molecule that is an alkene that contains a double bond. So we can either have that double bond between the first and the second carbon, or we can have that double bond between the second and the third carbon. And I'm going to go ahead and just draw lines to my hydrogen because I feel like I'm spending way too much time writing in all the little H's everywhere. So just understand that those are lines going to my hydrogens. Now real quick before we go on, you might be thinking, well, couldn't we also have the double bond between the third and the fourth carbon? Well, let's take a look at that. hopefully, once I've drawn it out, you can see that that's really just a different way to draw the first molecule. If we pick that molecule up, rotate it, and set it right back down, it's the same molecule. Okay, so that is not an isomer of this molecule. It is just a different way to draw the exact same molecule. And if it's the exact same molecule, it's got the exact same name. Okay, so we don't need to worry about naming that one differently. However, these two molecules are different. They are constitutional isomers. That is, they have the same molecular formula, but a different connectivity of atoms, and therefore they're going to have different chemical and physical properties. So let's just go ahead and write their molecular formula. C4H8, okay, for the formula of an alkene with one double bond, which is CnH2n. And same thing over here. I'll go ahead and write it again, C4H8. Okay. All right, so then the connectivity, let's prove to ourselves that they really do have different connectivity. For this one, we have a CH2. Start out with a carbon with just 2 hydrogen. And I'll draw a little arrow there. Maybe I'll do this in a different color. I don't want it to get too messy up here. Let's do it in green. So this first carbon is a CH2, carbon with 2 hydrogens. The next carbon is a CH, just has 1 hydrogen. Our next carbon is again a CH2, and our last one here is a CH3. Different than the way our carbons and hydrogens are arranged in this molecule, which starts out here with a CH3, followed by a CH, a carbon with just 1 hydrogen, followed by another CH, followed by another CH3. Okay, so the way that those carbons and hydrogens are connected is not the same. Same molecular formula, different connectivity of atoms, constitutional isomers. All right, so how do we name them? Because clearly they are different molecules, different chemical and physical properties. We have to name them differently. Life would be very, very confusing if these different molecules had the same name. Okay, an IUPAC nomenclature system is designed so that different molecules will always have different names. You should never come up with the same name for 2 molecules that are different by IUPAC nomenclature. So what we're going to do to name these properly is designate the location of the double bond with a number that's written before the name. Okay, so where is the double bond in this first molecule? Off of the first carbon. So we are going to call this not just butene, but 1-butene. Okay, over here, where is the double bond? It starts at the second carbon. Okay, so we're going to call this 2-butene. Okay, so remember that molecule that I erased? Let me go ahead and just draw it back again. I erased it because I said it's the same as the first one over here. Okay, I think I'll go ahead and just prove that to you by naming it. Okay, so we're always going to give the lowest possible number priority to the double bond. Okay, so we would not count this 1, 2, 3 and call it 3-butene. We would still count it from the lowest priority to the double bond. We would just count backwards in this case. 1, 2, 3, 4. So you see the name is still 1-butene. We just drew it backwards. I'll write this in parentheses over here. This is just kind of a side note. Okay. So we better come up with the same name because it's the same molecule. It's going to have the same chemical and physical properties. All right. So let's go ahead and erase here, and we're going to go ahead and talk about one more type of isomers called geometric isomers, which will apply to this example here for 2-butene. Single bonds can rotate freely. So in any molecule with single bonds, you can expect those bonds to be rotating, leading to different conformations of that molecule. So let's take butane as our example. 1, 2, 3, 4 carbons, all single bonds because it's an alkane. So this is butane. Okay. And I just happen to have a model here built for the 4 carbons, 1, 2, 3, 4, 1, 2, 3, 4, the 4 carbons in a butane molecule. I left off all the hydrogen just to make it a little bit more simple to look at. But all of these carbon-carbon bonds, these single bonds, are free to rotate. And so that leads to all sorts of different conformations for a butane molecule. So don't be surprised if a textbook or your instructor writes butane like this, where we're just showing that this bond has rotated, so this hydrogen and this CH3 have changed places. Okay. Both of these are still butane, 4 carbons connected in a row, consecutively in a row, but we would say these are different conformations of butane. So I'm going to write here, different conformations of the same molecule. Okay. And those different conformations exist because, again, those single bonds can rotate freely. Double bonds cannot rotate freely. Double bonds are locked in place. So if we take a look at a 4 carbon molecule with a double bond, let's just choose 2-butene. And I just happen to have a little backbone, 4 carbon backbone for 2-butene. So you can see my double bond here, and then these are single bonds. So we can get rotation here, but we cannot get rotation about the carbon-carbon double bond. It does not rotate freely. We can actually see that this leads to 2 different 3-dimensional arrangements about that carbon-carbon double bond. We can imagine another 2-butene where these 2 substituents are flipped. Okay, so let me redraw here 2-butene where the CH3s are both pointing up and the 2 hydrogen are both pointing down. In order to go from this configuration to that configuration, we have to break the double bond and reform the double bond, which is a little harder to do with these models than I wish it were. And therefore, it has to undergo a chemical reaction. And those 2 molecules will have different chemical and physical properties. They are not the same. So we can't name them both as just 2-butene. They have to have their own unique names because they are different molecules. And we name them as trans, I'm going to write it in blue here, trans 2-butene for the molecule that has the 2 larger substituents on opposite sides of the double bond, or cis 2-butene for the isomer that has the largest 2 substituents on the same side of that double bond. And these are related to one another as geometric isomers. Geometric isomers are isomers with the same molecular formula, same connectivity of atoms. Different than constitutional isomers. Remember, constitutional isomers had a different connectivity of atoms. Geometric isomers have the same connectivity of atoms, but they have a different 3-dimensional arrangement of atoms, about a carbon-carbon double bond. So again, same molecular formula. Both of these are C4H8. Same connectivity of atoms, CH3, followed by a CH, followed by another CH, followed finally by another CH3. But a different three-dimensional orientation about the carbon-carbon double bond. Either the largest substituents are on opposite sides of the double bond, trans, or the largest two substituents will be on the same side of the double bond, cis. So let's go ahead and write down here the definition for geometric isomers, sometimes called cis-trans isomers. Geometric isomers will have the same molecular formula, the same connectivity of atoms, but they will have a different three-dimensional orientation about a carbon-carbon double bond. So I'll write, but a different 3D arrangement about a carbon-carbon double bond. And I'll write in parentheses here, they're sometimes called cis-trans isomers. Okay. Now, here's the tricky part. Not all alkenes will exist as a cis-trans isomer pair. Some alkenes do not have cis-trans isomers, others will. So how do you decide if an alkene exists as both a cis and a trans isomer? Well, what you want to do, let's go back to the black pen here, because I want it to really stand out, is take a look at the two substituents on the carbons in the carbon-carbon double bond. So there will always be two other things attached to a carbon that is participating in a double bond. So I'm just going to write W, X, and Y, and Z, because I want to be generic here. If W and X are the same, or if Y and Z are the same, then that molecule does not have cis-trans isomers. Because you can imagine, if these are the same and you flip them, then you're still going to just have the same molecule. It's not going to change anything. Okay, so let me write over here. Let's write it in blue. If these are the same, or if these are the same. I'll write a little star here. If either side has the same two substituents, there are no cis-trans isomers. Okay. All right, let's go to the green. And I'm going to go ahead and erase this. So it doesn't have to be both sides the same. If either side is the same, no way, you don't have cis-trans isomers. If both sides are different, if W is different than X, and if Y is different than Z, then you absolutely have cis-trans isomers, because if you flip X and W, you get the different geometric isomer. You flip from the cis to the trans, or the trans to the cis. Okay, so let's write over here. If both sides have different substituents, there will be a cis and a trans isomer. I'm really running out of room here. Okay. All right, so we'll do a little more practice with that. Let's go ahead and erase here before we go on. Okay, so naming branched alkanes, we are on slide 5. The 4 steps for naming branched alkanes are written out for you already. I'm just going to read through those steps and I'm going to apply each step to a problem where we are going to name this molecule here, which has 2 branch groups. Okay, so first step, we want to name the longest consecutive chain of carbons. So you're going to count through, and I'll use a different color here, you're going to count through all the options you can come up with here. 1, 2, 3, 4, 5 would be pentane. 1, 2, 3, 4, 5 would still give you pentane. 1, 2, 3, 4 would be a shorter chain, so that's not an option. And let's see, 1, 2, 3, 4, that would again be a shorter option. So look at all the options and make sure you're coming up with the longest consecutive chain of carbons. In this case, the longest possibility is 5 for a pentane. Okay, so for step number 1, we come up with pentane as our longest possible chain. Step number 2, we're going to number that chain, that main chain or that parent chain, so as to give the lowest possible number priority to any branched groups. So if we number it this way, I'll number it a few different ways. 1, 2, 3, 4, 5. Then our branch groups are occurring at the 2 and the 3 position. Let's try some other ways to number this chain. So if we start from up here, 1, 2, 3, 4, 5, we still come up with 2 and 3. So those 2 ways of numbering are both equivalent. If we, let's go to the red pen, try counting it backwards, we can still come up with 5 by counting backwards, and I encourage you to try all possibilities because some instructors like to get really tricky and draw it backwards so that you have to number it in the reverse order. So it's always good to check the backwards. 1, 2, 3. We're not going to go down here for 4 because that would make it shorter than 5. So we're going to keep going, 4. And you could either go 5 here or you could go up and do a 5. Notice that either way, it's going to give you the branch group at the 3 and the 4 position. And the 3 and the 4 position are higher numbers than 2 and 3. So you don't want to number this particular one backwards. You want to go forward. Okay, so let's just stick with the blue because the blue numbering and the green numbering are actually equivalent. They're going to give us our branch groups at the 2 and the 3 positions. Okay, so now we're ready to go on to step number 3, and we're going to name our branch groups and identify their location with the number in the chain. So fortunately, the names for your branch groups are the same prefixes that we already learned when naming straight-chained hydrocarbons. So let's just go through those really quick here. If it's a CH3, it's the 1 carbon branch, and this line indicates that it's branched off of some larger molecule, then we call it a methyl. So remember, meth means 1. The YL ending tells you it's a branch group. If you've got 2 carbons, CH3CH2, again branched off of some larger molecule, then we use the prefix eth, so we call that branch group an ethyl. If we've got 3 carbons, CH3, CH2, CH2, as a branch group off of some longer chain, it's a propyl. Okay. Now, the 3 carbon branch group can either be connected at this end or at the second carbon. So I'm going to write one other possibility here, CH3, CH, CH3. Okay, so it's still 3 carbons, so it's still a propyl, but we call this an isopropyl group. Iso for same, it's got symmetry, you've got a CH3 and a CH3, so an isopropyl, still 3 carbons, still a branch group, so prop for 3 and the YL ending tells you it's a branch group. Now you can go on, butyl and pentyl and etc., but it starts to get a little more complicated with those larger branch groups because just like the propyl, you have different ways of attaching those 4 carbons and those 5 carbons. So I think these 4 are good for an introductory chemistry class. I'm going to stop right there, just these 4 branches. That's all we'll see in our problem sets and any problems that we work in this tutorial. All right, so then we go back over here and we look at our branch groups, and we're using the blue numbering here. So that means that we've already named this chain as pentane. That means that this is a branch group and this carbon is a branch group off of that longer pentane chain. We've got a 2-methyl, 2 because it is at the second carbon of the pentane chain, and we have got a 3-methyl. 3-methyl because it's at the third, it's off of the third carbon of the pentane chain. So I'll write for step number 3, we've got a 2-methyl and we've got a 3-methyl. Okay. Rule number 4, and this is our last rule, and it's kind of a long one, so I'm going to go ahead and make sure I read it and get it all in there. Don't forget anything. Write the full name as a single word. Use hyphens to separate numbers from prefixes, so numbers from letters. Use commas to separate numbers from other numbers. Use alphabetical order for multiple branch groups. So for example, ethyl would be listed before a methyl because E comes before M in the alphabet. Use di, tri, and tetra prefixes if there are multiples of the same branch group. So we are not going to say 2-methyl, 3-methyl. We're going to put it together and say 2,3-dimethyl. Okay. But in the alphabetical order, dimethyl still counts as an M alphabetically. Okay. So that can get a little bit confusing. So step number 4. We're going to write this full name as one word. We have a 2, 3. Remember, we separate numbers from other numbers with commas. Don't forget the comma because it's not going to have 23 methyl groups. It's got one at the 2 position and the 3 position. It only has 2 methyls. So 2,3-dimethyl. Okay. So dimethyl, there's 2 methyl groups. Where are they? One's off of the second carbon of our longer branch, and one is off the third carbon of our longer branch, and it's a dimethyl pentane, all one word. Okay, so again, just to really reinforce, this tells you that there is a parent chain of 5 carbons with single bonds between them only. It's an alkane. Off of that 5 carbon chain, there is a 1 carbon, because it's a methyl, a 1 carbon branch at the 2 position and a 1 carbon branch at the 3 position. Okay, so we will work lots and lots of problems going back and forth between structures and names and structures for branched alkanes in our problem set, but I don't want this to get too long, so I'm going to go ahead and move on now to the nomenclature of branched alkenes and alkynes, which is slide number 6. So once again, I have all of the steps for writing the name of a branched alkene or a branched alkyne written out for you on slide 6. So I'm going to just read through these steps and apply each step to naming this molecule, this branched alkene that I have drawn up here on the board. So starting with step number 1. Step number 1, you're going to name the parent chain. That is the longest consecutive chain of carbons that contains either the double or the triple bond. So if there's a longer chain of carbons, but it doesn't count through the double or triple bond, then it's not your parent chain. It has to count through the double or the triple bond to be your parent chain. So just like we did with the branched alkanes, you want to consider all options and make sure you're getting the longest continuous chain of carbons. So if we start in the forward direction, 1, 2, 3, 4, 5, 6, we get a hex. If we start from up here, 1, 2, 3, 4, 5, 6, we still get hex. We still get 6. If we count reversed, 1, 2, 3, 4, 5, doesn't matter if we go up or down, we would get, again, 6. We would get hex. And it's got a double bond, so we know that it's a hexene. So I'm going to go ahead for step number 1. I'm going to write that we have a hexene. Okay. Step number 2, number the chain giving the lowest priority to the double bond. So we had a couple ways to number it. Okay. The lowest possible number that we can give to the double bond is going to be when we count the forward direction and give it a 2. It doesn't matter if we started here or here, the double bond is going to occur at the 2. We don't want to count backwards because then our double bond occurs at the 4 position. And the 4 position is higher than the 2. So we can see on step 2 that we have a 2 hexene. Okay, so on to step number 3. Assign the names to any branch groups, the name and the number to any branched group. So let's go ahead and call this chain our 2-hexene. You could have also used this carbon. You're going to get the same name. It doesn't matter if you count it from here or here. But I like to go ahead and circle the 6 carbons that I've already named as 2-hexene so that I can see that I'm only naming this one little carbon, this one little CH3 as a branch group off of that 2-hexene. Okay. All right, so what number is it? It occurs at the 2 position and it's 1 carbon, so it's a 2-methyl. Remember, meth means 1 carbon, the YL ending because it is a branched group only. All right, step number 4. And I'm going to go ahead and read this because again, there's a lot to number 4. Write the full name as one word. Use hyphens to separate numbers from prefixes, so numbers from letters. Use commas to separate numbers from other numbers. Use alphabetical order for any branch groups. We only have 1 in this example, but let's say that we see an example later where we have both a methyl and an ethyl. The ethyl would come before methyl in the name because it's alphabetically listed. Use di, tri, or tetra prefixes if there are multiple of the same branch groups. And if it is an alkene, determine if cis-trans isomers applies. All right, so let's go ahead and put this all together for number 4. So we have a 2-methyl. We're going to put a hyphen here, 2-hexene. Cis or trans, let's go over and double check. And I'm going to use the red pen so that it really stands out here. To check for cis-trans isomers, remember we want to look at the 2 substituents on this carbon of the carbon-carbon double bond. If they are the same, which they are, this one's a CH3 and this one's also a CH3, then it doesn't matter if we flip them. we're going to get the same molecule. So therefore there are no cis and trans isomers for this particular alkene. It doesn't matter that the other side is different. This is a hydrogen and this is a CH2, CH2, CH3. If just one side has the same two substituents on the carbon of a carbon-carbon double bond, then there's no cis-trans isomer. Because again, you can flip their position and you're still going to have the same molecule. It won't change. Okay, so we kind of got off lucky on this one. We don't have to decide if it has, if it's a cis or if it's a trans isomer. It doesn't have cis-trans isomers. That means that our final name is 2-methyl-2-hexene. Okay, so I like to go through it one time, just kind of the reverse order, because in the problem set, we're going to be taking the names and converting them into drawings as well. So 2-methyl-2-hexene. This means that we have a 6-carbon chain with a double bond at the second carbon, starting at the second carbon. Also off of the second carbon, we have a branched group that is just 1 carbon long. It's a methyl, so just 1 carbon long. All right. Let's go ahead and erase here, and we're going to go on to slide 7 and learn about a slightly easier and faster way to draw these molecules. We know how to draw Lewis structures to represent molecular compounds. Remember that a Lewis structure is going to show every single covalent bond between every single atom in that molecule. It's going to show how those atoms are connected. But we've already really seen how this can get to be very tedious when you're drawing larger molecules and you have to draw in all of those atoms and all of those bonds. And so chemists have a much faster way to draw organic compounds. We have 2 other choices. We can draw condensed structures or we can draw line structures. Okay, so let's go ahead and just draw a Lewis structure out. It's going to take us a little while for 2-methyl-heptane. Okay, so hept is 7, 1, 2, 3, 4, 5, 6, 7. 2-methyl, doesn't matter if you go up or down, I'll just go down with a 1 carbon branch, so 2-methyl. And then I'm going to go in and draw all my lines to my hydrogen. And really, for a proper Lewis structure, I should draw in all of my hydrogen. Okay, so fairly tedious. I think you will agree that that is getting to be quite tedious. One, 2, 3. Okay, I did it. All right, so let's go ahead and convert this instead into a condensed structure. And a condensed structure is going to show your carbons and hydrogens, but none of the bonds between them, except for double bonds between carbons and triple bonds between carbons. And then it'll also show bonds to branched groups. So it's not going to show any of the bonds in your main chain or your parent chain. Okay, so I'm going to write here, only shows bonds to branched groups or double and triple bonds. Okay, so when we convert this into a condensed structure, we're going to just write CH3 for this first carbon and 3 hydrogen that are attached to it, followed by a CH. This carbon just has 1 hydrogen. Now we're going to go ahead and show the bond to the branch group, which is a CH3, and then we're going to go on and write our CH2 for the next carbon, another CH2, followed by another CH2, another CH2, and finally a CH3. Now, an even shorter way to write this would be to just write that you have 4 of these. So we would write that as CH3, CH, gotta show the bond to the branch group, which is a CH3 here. And then we'd write parentheses. We have 4 of these, 1, 2, 3, 4, and then another CH3 at the end. Okay. All right, so that's how you write a condensed structure. But even faster and more convenient are going to be your line structures for organic molecules. In a line structure, the points all represent carbons. Your hydrogen are just assumed for octet. The only atoms that you're actually going to write in would be atoms that are not carbon and hydrogen. So you would write in if there was an oxygen or a nitrogen or a sulfur or a halogen or something other than carbon and hydrogen. You show double bonds and triple bonds, and you also show molecular geometry. So very convenient, nice way to show the molecular geometry with a line structure. So let's write here for line structure. We underline condensed so it doesn't get too messy here. For line structure, just write line. All points represent carbon atoms. Hydrogen are assumed for octet. Atoms other than carbon and hydrogen are written in. So I'll write here O, N, etc. Those would be the only ones that you would actually write in to the structure. Okay, so let's take this example again and turn it into a line structure. All right, so take your pencil or your pen and set it down. Okay, that's your first carbon right there. You didn't even do anything, but that's a carbon. Okay, now you can either go up or down. I always go up. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. And we're trying to show 1, 2, 3, 4, 5, 6, 7. We're trying to show heptane. So 1, 2, 3, 4, 5, 6, 7. There's my 7 carbons in my heptane chain. Now what about my branch group? It's a 1 carbon branch and it's off of the second carbon. This is my second carbon, so draw a line coming out from there to represent another carbon. All your hydrogen are just assumed for octet. So if you're looking at this structure, we can see 1, 2, 3, 4, 5, 6, 7 carbons in our heptane chain, 1 carbon for our branch. It would just be assumed that this carbon, because it's only bound to 1 other carbon, must have 3 hydrogen, octet. This carbon must only have 1 hydrogen because it's bound to 1, 2, 3 carbons. It can only have 1 more bond to hydrogen. This carbon is only bound to 2 carbons, so it must have 2 hydrogen. Same thing with this one, and this one. And then over here at the end, our terminal carbon just has a single bond to a carbon atom, so it must have 3 hydrogens to complete its octet. Okay, so we will get lots more practice with condensed structures and line structures, especially line structures, because they are going to be so important in organic chemistry. To help you save time to draw things in line structure will be really important. So we will do lots of practice problems in our problem set, but for now we're going to go ahead and move on to our final slide, which is slide 8, and talk a bit about cyclic hydrocarbons. 3 or more carbons can be connected in a ring structure, making up a cyclic compound. So if we've got 3 carbons connected in a ring, each carbon would have 2 hydrogen, In a line structure, nice and easy way to draw this. It's just a little triangle. Remember, every point is a carbon and then the hydrogen are assumed. And to name a cyclic structure, you just take the regular name, for in this case the alkane, and you tack on the prefix cyclo. So for a 3-carbon alkane, we have the name propane. So we would call this cyclopropane. 4 carbons connected in a cyclic structure would be a cyclobutane. 5 carbons would be cyclopentane. And 6 would be cyclohexane. That's an X there. Okay, so I'll stop there. I think you probably get the idea. The one last thing I want to say about cyclic compounds, because we are going to start to see a lot of cyclic compounds when we get to the biological chemistry portion of these tutorials. So the last thing I want to say is that the bond angle, I'll go to a different color here, the bond angle required in some of these smaller cyclic structures is going to be highly strained, making these molecules unstable. So for example, in a cyclopropane, this bond angle would have to be 60 degrees, much more compressed than that typical tetrahedral geometry where carbon has 4 bonds that are 109.5 degrees apart in 3-dimensional space. So this is highly strained. It's going to be 90 in cyclobutane. So again, much more compressed than that tetrahedral geometry of 109.5 degrees. It's not until we get to 5- and 6-membered rings that we start to see a bond angle close to 109.5. So these bond angles are close to 109.5 degrees. And these structures are not actually going to be flat, 2-dimensional. They're going to be kind of jagged, so they're not going to lie in one plane. So that helps as well. They're sort of puckered. These carbon angles here are sort of puckered out. So they're about 109.5 degrees in 3-dimensional space. So when we look at biological molecules that have rings, we're going to see lots of 5- and 6-membered rings because these ring sizes are going to be more stable. They can accommodate that bond angle, that 109.5, approximately 109.5 degree bond angle of a tetrahedral geometry. Okay. All right, so this will conclude our tutorial 16. I hope you will consider tuning in to problem set 16. We have lots and lots of problems on naming and drawing hydrocarbons. Thank you.